The topic that we are going to see today is multivibrators. In the last class, we have seen the oscillators. Before that, we have seen the amplifiers. These amplifiers, oscillators, and also these multivibrators have got to do with the feedback that we employ, okay, in an amplifier. If there is no feedback at all, it is open loop. When there is feedback, there can be a positive feedback or negative feedback. For amplifier, when it comes to controlling the gain, which type of feedback is required? Anybody? For an amplifier, when controlling the gain is required, what type of feedback is necessary?
Negative
Negative
feedback.
feedback.
Very good. Now, in oscillators, we have to generate the oscillations with sufficient amplitude. That means we start with no signal. No signal means there will be some noise. So that noise has to be amplified to to a level where it is sufficient enough. Okay. So there we employ the positive feedback. Similarly, this multivibrator is similar to the oscillations. This multivibrator is similar to the oscillations, but the difference is in oscillators we can generate sinusoidal oscillations. Understand what I mean is this? Everybody see here. I can generate sinusoidal oscillations when it is oscillator, but in multivibrators, most of the times it is the square wave or rectangular wave generations. Okay, so there is a difference. So in oscillators, it can be this or this in general, whereas in multivibrators, it has to be the square wave or rectangular wave waveforms. Okay, so that is what multivibrators are. Fine, we shall see what this is in detail, point by point now. So there are many occasions when we require a square wave output. So this is square wave output from an oscillator rather than a sine wave output. This is sine wave output. Okay. So multivibrators are a family of oscillator circuits that produce output waveforms consisting of one or more rectangular pulses. Yeah. So microvibrators, multivibrators are family of oscillators. They belong to the family of oscillators, but they are the ones which produce, okay, output waveforms consisting of one or more rectangular pulses. So this is what they mean. Fine. So they are nothing but the oscillators, but in particular, if you have to go, they generate the rectangular pulses or square pulses like this. Understand the difference between the oscillator and pulse and the multivibrators now? Okay. Now, they are referred to as multivibrators. Why? See, the term multivibrator originates from the fact that this type of waveform has multiple vibrations. They are all vibrations only. See, this is one vibration, goes to maximum, comes to minimum. Again, it will stays there at minimum for some time and again goes to maximum. After going to maximum, again it stays there. So that is what there are multiple such things happening. That's why it is called as multi-vibrator, or it has been derived from the word multiple vibrations. Okay, in other words, we can say they have rich harmonics. They are rich in harmonics. Harmonics means what? Generating the vibrations of the same frequency. Okay, so they have multiple such waveforms with the same frequency. So that it is called. It is said to have the large harmonics. Understand that? So multivibrators are those which generate multiple vibrations, or in other words, they have or they are rich in harmonics. Fine. And what type of feedback is needed for multivibrators? As it is, as it belongs to the family of oscillators, a positive feedback is required for multivibrators also. Understand that? So understands here, family of oscillators. These multivibrators belongs to family of oscillators. That's why this also should employ positive feedback. Fine. Now, depending on, okay, depending on what types of these vibrations they produce. That means depending on the stable states. Now we come across something called as stable state. Stable states. How many states are there if you take this type of signal? Let me write that. How many states are there here? How many different states do you see here, or levels do you see here? Anybody? So this is 0, this is 1, 0, 1, 0, 1, or high or low. So how many such states are there? There are two states. Everybody understand which are those states? High state is one, low state is other. High state means it is logic 1, and low state means it is logic 0. So we'll be talking about this logic 1 and logic 0 in digital electronics in next module. Okay, but this is part of digital electronics as well as analog electronics. Understand that? So since we are generating the rectangular or rectangular, why they call it as rectangular? Sometimes the 0 can come for this duration and the 1 can be there for larger duration, and again 0 can be there for small duration, and it can be there for longer duration, and suddenly this can be there for longer duration and this can be there for. So this is why it can also be called as rectangular what waveform, whereas here 1 is there for longer duration, 0 is there for shorter duration. They are these states. Logic 1, logic 0 are two states. Okay, and depending on which of these states are stable. Stable means what? Stable means what? Stable means which are the states which will be at that condition itself without external input up, applied. What I mean is this: stability means no change. Stability is no change. If a state is there without any change, it is stable state. So depending on how many states are stable, or are there any stable states or no stable states at all, so depending on all those, we categorize these multivibrators as here a stable multivibrator. Then we also call it as monostable multivibrator. Okay, and the third type is bistable multivibrator. Okay, now if you see the names monostable and bistable, what do you understand? What is monostable? I'm talking about stability now. Yeah, I talk about stability or stable states or stable states. Okay, so when we are talking about that, by listening to the term monostable, what do you understand? What is mono there?
There is only one high or low.
There is only one stable state. Monostable means one stable state. Okay, let's understand. Monostable means one stable state. Whether it is 0 or 1, it depends. There's just one stable state. It's state. Similarly, if you come to bistable, what is it? There are two stable states. Okay, and if you come to astable is, anybody can you guess what is astable? Astable. Stable is,
No stable state is there.
very good. No stable. It's opposite to stability. So no stable state in astable multivibrator. Understand that? So here in astable multivibrator, we have no stable states, whether it is 0 or 1. There are two states, both 0 state as well as 1 state are not stable. Whereas in monostable, either state 1 or state 0 could be stable. In bistable, both are stable. Understand that? So how to make out that? We all have understood that multivibrator, if you take in general, multivibrator, if you take, it generates such waveforms. Okay, now astable, if you take astable multivibrators, yeah, no state is stable. That means this is 0 state. Without we doing anything, it goes to 1. It will stay there for some duration and it will again come back to 0. We are not doing anything. It is all happening by itself. It will be 0. It will stay there for some period and again becomes 1. It becomes 1, stays there at 1 for some period and again becomes 0. And we don't have control over this. This will keep happening by itself. Understand that? So that's why it is referred to as free running multivibrator. See this? Stable multivibrators are also called as free running. They're all free running. We don't have control over it all. Unless we switch off the circuit, unless we cut the supply to the circuit, these free running oscillations will continuously be there. We don't have control over this. We don't apply even the external trigger to stop the oscillations or do something regarding this. There is no external input at all in unstable multivibrators. Understand? So they are called as free running oscillations. They become zero, they one, zero, one, zero, one, zero, one. Continuously they'll be becoming so, but they'll be switching between zero and one. Okay, and they are called as free running oscillations, and free running oscillations are present in a stable multivibrator. Free running means no stable state. Zero is also not stable, one is also not stable. It will be at zero for some time and suddenly it changes to one. It will be at one for some time and suddenly changes to zero again. It will be there at zero for some time, again changes. So there is no stability at all. It's not stable at all. Zero, one, zero, one. It depends on the time. Okay, duration. It will there be for some duration and without our interference. Okay, it just changes its states. Fine, that's why it is there is no control over change of state. So no change is no state, whether it is zero or one, is stable in a stable multivibrator. Is this okay with you now, everybody? Is it okay with you? Fine. Now the second one that we are seeing, this is A. The second one that we are seeing is monostable. In monostable, what's happening? Suppose a state is zero. Suppose a state is zero. It will continue to be at zero because this is a stable state. Suppose zero is stable state and it will continue to be at zero state. Suppose if this zero state has to become one, who should decide that? The designer should decide that. The person who wants the output to be of some nature, he should decide that. Get that point? Okay, now as a designer, I'll decide, I'll give a triggering pulse here. This is called as triggering pulse. Triggering pulse is of very small width. It will just come here and it will again go off. Here, it will come at this instant of time. At this instant of time, it will come and it will again vanish. That's a triggering pulse. So this is called as triggering pulse, which we need to supply externally. This is triggering pulse and we need to supply it externally. So when we trigger this zero, then it will become one. But this one will not be there for a long time. It will there be for some duration and it will come back to zero again. So which state is stable here? Can you make out? We don't have control over one. Okay, but zero is there till we apply the triggering pulse. So can you tell me which state is stable among zero and one?
Zero.
Zero is stable. So between 0 and 1, 0 is stable because unless we apply any triggering pulse, it will be 0 forever. Once we trigger it, it will become 1 and this 1 will not be there for a long time. It will be there as 1 for some duration and suddenly again it comes back to 0, and when it comes back to 0, it will continue to be 0 for the period till we bring in another triggering pulse. Again, when another triggering pulse, it goes to 1, but it will not stay there at 1. For some duration, it will be there, but again, it will come back and stays at 0 till we apply our third triggering pulse. Is this okay with you, everybody? This is what is called as monostable multivibrator. In monostable multivibrator, only one state is stable, okay, and the other state is unstable. So when it has to go from stable state to unstable state, we have to apply a triggering pulse, and when it goes to the unstable state, it will be there in unstable state for some duration and it will come to the stable state by itself. Okay. Everybody is okay with that? Now do you have anything to ask here? One question can raise, one question can come to everybody's mind. What is that? What question can come to your mind? Anybody?
Sir, why we have to apply the triggering pulse?
Why we have to apply this triggering pulse? Unless we are happy with, unless suppose, let's say we are okay with this pulse. What is that pulse? We are okay with this pulse continuously going zero. It is zero, continuously zero. If it is continuously zero, it is of no use to me. Okay, now I think whenever I want, this zero should become one. Whenever I want, this zero should become one, and then again it should come to zero by itself. So if I have such applications, if I have such requirement, then this monostable multivibrator will help. Now your question will prompt me to discuss about the applications of monostable multivibrator. Okay, now where does this application come? Where do you find the application of monostable multivibrator? Let's see now. See here. Now suppose there is an application. Suppose there is an application which is not automatic. Unless we say something, it will not do anything. Okay, so what we do is we keep something off for some duration. We keep something off for some duration, and unless there is something externally triggering it, it will never become one. It will never become on. It will be there as one for some duration, again it becomes zero. So that means wherever you need something to go on, only when you want it, okay, you need monostable multivibrator. It will be off for any duration unless we have applied the triggering pulse. Once we apply the triggering pulse, it will become one. Now why we are applying triggering pulse? We want triggering pulse to say at what time we want this zero to be one. At what time we want this zero to be one, and when this is one, do this operation. When this is zero, don't do this operation. Where do you come across this this necessity? Anybody? Can you just name an application where this type of timing constraints are there? Initially I want it to be zero, but when I want, it has to do some work. What is it? Anybody? Do you know time bomb? Now time bombs you've heard of, right? Time bombs where we set the timing, okay, and when the timing is reached, then only it should blast. Okay, it's a timer. It's a timer. So wherever we need timer to be employed, we come across something called as monostable multivibrator. Okay, it has to be off for some duration. Say I set the time for 10 minutes. For 10 minutes it should not blast. When the 10 minutes are over, suddenly this I'll apply an external trigger. So this will become one, and when it becomes one, okay, there has to be a blast. So this is an application. Time bomb is an application. Understand that?
Sir, how much time it requires to get it triggered?
How do we know? No, what is your question?
How much time it requires to trigger when the triggering pulse is applied? How much time it requires to get to the one from zero?
How much time it gets? It is very small time. It takes some time to go from 0 to 1, but that time is in millisecond, microsecond. It's very high speed, so it becomes 1. Is that what you're asking?
Yes, sir. And how much time will spend at one?
How much time it
It
will
answer
spend
this.
at 1 is designed by using RC circuit. In the circuit we have got, see here, in this circuit we have got this R and C, right? So this R and C, so this R and C will decide how long it will stay at 1. Understand that? You're talking about this, right? If it becomes 1, how
Yes,
long it
sir.
will stay at 1? So this can be designed by using RC values. Okay, so that we design in the circuit. So for that duration, it will be 1, and again it will come back. And soon after it comes back, it will go 1 only when I apply external triggering, and it will again stay there for the duration that I have designed using RC circuit. That is this circuit. So I'll come to this.
Sir,
Next, I'll
can
be
it be applied multiple times?
we can what?
Can it be applied multiple times?
We can apply the trigger multiple times. So that is what I'm showing you here. We can apply trigger any number of times. It all depends on the application. Understand that? If there are series of bombs to be blasted, they're all connected with a wire, but each bomb has to be blasted at a duration after every 10 minutes. After every 10 minutes, there has to be a bomb blast. So all the bombs are connected. The first bomb I have set the triggering pulse to be after 10 minutes. The second bomb, I'll set the triggering pulse to be at 20 minutes, so that after 2 such durations, the second bomb should blast. So there you find such monostable multivibrator. Is that okay with you now? Fine.
Excuse me, sir.
Yeah, go on.
Sir, the time we set in bomb is equals to triggering pulse we give in a
No.
like this.
The time we set is depending on the trigger pulse that we want to apply, and this can also be made automatic. The triggering pulse that we are applying externally can also be made automatic. So this can also be programmed. The external trigger that we are applying, that also can be programmed. How? Here in the input, we can have this type of waveform. So this can be designed for 10 minutes. This has to be 0. At 11th minute, when it becomes 11th minute, okay, it has to go put an input, give 1, and again become 0. So this type of things we can design using multivibrators only. So this itself is the input, and depending on this input, we can generate monostable output. Okay, so in time bomb, the triggering pulse duration is not important. In time bomb, the duration for which it is being 0 is important, because in this, when it is 0, it should not blast. The moment it becomes 1, it should blast. Understand that?
Okay, sir, I got it.
Fine. Now, if we come to the bistable multivibrator, in bistable multivibrator, both the states are stable now. Both the states stable. Now here only one state is stable. Okay, you have both the states stable in bistable. What happens in bistable? Here I'll write for bistable here. The output is 0 for some duration. When I give a triggering pulse, it will become 1. And when it becomes 1, there also it is stable. How long it is 1 now? Till another triggering pulse is applied. Then it becomes 0. And it will stay at 0 for the duration till I apply a triggering pulse. It becomes 1. And after it becomes 1, okay, it will stay there forever till I apply triggering pulse. That means for 0 to become 1, we have to apply triggering pulse. For 1 to become 0, there also have to apply the triggering pulse. So how many times a triggering pulse is being applied in one clock duration? One clock is 0 to 1. From here to here is one clock cycle. Okay. For 0 also, for 0 to become 1 also, you need a triggering pulse. For 1 to become 0 also, you need a triggering pulse. Is that okay with you? That is what is bistable. Is that understood now? Okay. So what is the difference between monostable and bistable? How many times when were you applying triggering pulse in monostable, and when you are applying triggering pulse in bistable? Can anybody?
To make it unstable in monostable, to make it unstable, we have to apply the triggering pulse. But in bistable, we have when to make it stable also we have to apply triggering pulse.
No. Let me explain like this. Let me explain like this. See here now, everybody. From stable to unstable, it is going. Okay. Stable to unstable. Unstable state is 1. when I say unstable, it will come to the stable state by itself. Okay, so we are just applying one triggering pulse to make it one. From 1 to 0, we don't have any triggering pulse. But whereas here in bistable, from 0 to 1 also there is triggering pulse. From 1 to 0 also there is triggering pulse, because 0 is also stable, 1 is also stable. So when 0 is stable, everybody done. When 0 is stable, okay, for this to become 1, we need to apply the triggering pulse, then it becomes 1. This will be 1. This 1 is also stable state. Till I apply another triggering pulse, it will not become 0. Only after application of triggering pulse, it will become 0. So this is what is bistable. Okay, so we have learned what is astable, what is monostable, what is bistable. In astable, there is no external triggering pulse at all. It is free running oscillations. It will stay there at 0. By itself, it will become 1. It will stay there at 1. It will by itself become 0. Okay, so free running. So astable is free running, whereas in monostable, it is just one state. In bistable, both the states. In monostable, we have written this, right? In monostable, even this can happen. One can be stable state. One can be stable state. After applying the trigger, it can become 0. It can stay at 0 for some duration. Again, it can become 1. So 1 is stable, 0 is unstable. That can also happen. In monostable, there are two cases. Both things can be done. Even 1 can be a stable state, or even 0 can be a stable state. When 0 is stable state, 1 is unstable, and when 1 is stable, 0 is unstable. So that is what monostable is. Any one state can be stable. It's not that both 0 and 1 has to be, or it's not that only 0 has to be stable, 1 has to be unstable. No, it's not like that. Any state can be stable, or any state can be unstable in monostable multivibrator. I hope it's clear to you now. Now, after understanding all this, let's move on with an example of a stable multivibrator. This is very important circuit diagram for understanding now. Yeah, Pratika, you have something to ask. Go on. Pratika, you have something to ask there? You have raised your hand. If no, if it's by mistake, it's fine. Okay, now let's understand this now. Everybody just see here. Everybody just see. There is an output. There is an output. Okay, and this is output of a op-amp. Fine. Now this output is being fed back to the input. Which type of input we are feeding it back? Inverting or non-inverting?
Non-inverting.
Non-inverting. So if we are feeding back to the non-inverting amplifier, the output and input, what is the phase shift between the output and input? What is the phase shift between this output and the input here? What is the difference in phase shift between these two?
0.
0. Because this is non-inverting terminal. Okay, so this is output of output. So input is non-inverting terminal and output is here, so there will not be any phase shift. So which means that which type of feedback is this?
Positive.
Positive feedback. Now see here. Now there are two resistors here. Two resistors. Fine. If there are two resistors, using voltage divider rule, here this is R1, this is R2, and this is V out. This is R1 and this is R2, and they are taking the output from here. They are taking the output from here. So that means when R1 and R2 are connected here, this V out gets divided between R1 and R. That means some part of this V out comes across R1 and the remaining part of this V out comes across R2. So R1 and R2 are actually voltage dividing circuit. So they form voltage dividing circuit. Now, what is this voltage? What is this voltage I'm writing? So this voltage is total voltage into resistance of the branch where the voltage is falling. So where it is falling across R2. So this is the voltage I'm talking. What is the voltage across this? Is this. Okay. Now, divided by sum of the resistors. So this voltage is being fed back to the non-inverting terminal. It is some voltage. Let's say this is the voltage across V2. So V2 is this. Everybody understand this point? So we have V2 here. V2 by voltage division rule is given by total voltage into resistance where V2 is dropping divided by sum of the resistances. So this is what is the what equation for V2. So that V2 comes here. That V2 comes here. Fine. V1 is the voltage drop across R1. V2 is the voltage drop across R2. And this V out is V1 plus V2. So this and this together will form V out. That means I'm just taking a part of V out and giving back to the non-inverting terminal. Now this output would be plus VCC. Everybody understand this? This output would be plus VCC when this V2 is greater than the voltage across the capacitor. Let's say voltage across the capacitor is VC. Let's write it like this. Voltage across the capacitor is VC. Okay. Now, when VC is less than V2, voltage across the capacitor looks like what? Yeah, this is voltage across the capacitor. Yeah, in this waveform, I'm marking in red, right? So that is what is voltage across the capacitor. This is voltage across the capacitor. When this voltage across the capacitor, okay, is greater than or less than, we can decide. So when you see here, so it just goes like this. Okay. And what is V2? V2 is this. And we shall call this as the upper threshold voltage. We shall call it as upper threshold voltage. What is upper threshold voltage? Upper threshold voltage is the voltage that comes here across the capacitor. Okay, across the capacitor we have some voltage. So when it reaches the upper threshold voltage, so that is this. When it reaches the upper threshold voltage, okay, so it becomes greater than V2. When voltage across the capacitor becomes greater than V2, who is dominating? Inverting terminal is dominating or non-inverting terminal is dominating? Anybody? Who is dominating? When VC is greater than V2. Can you speak? When VC is greater than V2, inverting terminal is dominating. When inverting terminal dominates, what would be the output? Output would be minus VCC. When the non-inverting, when V2 is greater than VC, V out is plus VCC. That is what is happening here. See here, from this point to this point, from this point to this point, okay, this voltage across the capacitor. See here, this is voltage across the capacitor. Something that I've marked in red is voltage across the capacitor. So voltage across the capacitor is less than this. So when it is less than this, V2 is greater. So it becomes plus VCC. Now after this point, what happens? It is going beyond this. And when it goes beyond, again, the charging starts, charging stops, and discharging starts. So when the capacitor is discharging, obviously voltage across the capacitor, what would happen to voltage across the capacitor? When the capacitor is discharging, what happens? Anybody?